Hello students, welcome to EduCell. In this video, we are going to discuss about the weighted vertex cover using pricing method. So here in this video, we have to first segregate the total content into three different halves. First, we have to discuss like what is weighted vertex cover. Next, how we will find it out using pricing method. Next, the approximation pricing method which we have used. How much approximation towards the optimal solution, we will discuss that one using the mathematical equations. Okay, those who are new, kindly watch the previous videos related to the vertex cover. How do we find it out using independent set? Also in reduction that we have discussed, also I have kept one video like how to find out the approximation vertex cover. Like it is two approximation, we have also discussed that time. Here the weighted vertex cover, something different that we are going to discuss in this video. Okay, so the first definition, it says the vertex cover definition. Okay, the given graph G, which a set of vertices, set of edges. Here a vertex cover which is S, it should be a subset of V. V is a set of all the vertices such that each edge E has at least one endpoint to S. Suppose you have selected, you can say I'm just writing the set cover or vertex cover. Here V is, I'm just writing a graph through which, after making a graph, you can understand the concepts we are going to discuss in this video. Like there are four vertices. I must tell the vertices are A, B, C and D. There are four vertices we should have to keep in mind. Next is the edges. Based on the edges, there are also A to C, A to B. I'm just writing the edges in this format. A to B, A to C. Next, C to D, B to D and C to D. B to D and C to D. Clear? So this represents the vertices, a set of vertices and set of edges. Suppose you are trying to find out a vertex cover. Vertex cover, like we have already discussed, the minimum number of vertices we have to find it out which cover all the edges. Okay, suppose I am picking A and D is our vertex cover set as S here, A and D. You can take the same as B, C also. Clear? So here in A and D, suppose we are trying to find it out, AC is covered and AB is covered, CD is covered and BD is covered. As per the definition, at least one endpoint of S means, so this is an edge. For A, if I am picking, A is one endpoint of the edge and A to B and A to C also one endpoint. For D, suppose I am finding out, here for B to D one endpoint and C to D is one endpoint. So this is what our vertex cover is. Next, for the weighted vertex cover, when we decided to find it a weighted vertex cover, weighted means a weight assigned to a vertex. That's why we are saying, whenever we are saying the vertex cover, we should say a weight assigned to a vertex. Then only we can operate on the vertex cover. If the weight is not assigned, we cannot find a weighted vertex cover. Okay. So the vertex cover, basically we have an example here, like which is having the weight, the sum of the weight. Suppose this is just a vertex cover 1, VC1 I am writing. So the weight it covers are like 2, 2 and 4. Clear? So total is 8. Here VC2 I am just saying these are two different vertices we are having. So based on these two, we have the weight as 11. So the minimum is this one. So that's why we are saying the minimum weighted vertex cover is VC1. So our main objective is exactly to find it out. So the definition for the weighted vertex cover is like the graph we have G, V and E with the weight assigned to the vertex which is a positive weight. Basically it's equal to 0 or greater than 0 that we have discussed. It's said to be a positive weight assigned to a vertex. Okay. Next, a minimum weight subset we are trying to find out, which is set S that belongs to a vertices set. Next, every edge incident to at least one of the vertex, like what we have recently discussed in the definition, is similar to the definition, but one thing they have added is weight. Okay, so the same two examples I kept for the two examples for the vertex cover. So this is our VC1, this is our VC2 vertex cover 2. Based on the total weight, here they have taken five vertices, five vertices. Here in this case, they have kept four vertices to cover the to be said as vertex cover, but the weight they have said as 57, and here the weight they have found out by adding all the weights there inside the vertex cover 1 set. So this is 55. So definitely our target, our objective is, our main objective is, I'm just writing that one, aim minimum. Here I'm just naming that one WVC, means weighted vertex cover. Our target is, our goal or aim and objective, you can say, aim is minimum weighted vertex cover, means the weight we are getting, that should be minimum. Here we are trying to find it out. Then the approach we are exactly following is pricing method. So that's why we are going to discuss the pricing method. Okay, the main reason here is that though we are not getting the optimal, so we are trying to approach towards the optimal. Here the approximation we have used as pricing method. Okay, so in pricing method, what extra they have used, like each edge must be covered by some of the vertices, or some of the vertex that we have already discussed earlier. Also, edge pays at least a price, you can say the weight assigned to an edge should be greater than 0, means which is an you can say it's a positive value. Clear? So suppose there is an edge I here and J here, the PE represents, it's a basically the cost or weight assigned to an edge, as we have seen in a weighted graph. In a weighted graph, the weight assigned to an edge, this is what exactly we are focusing here. The fairness condition represents edges incident to a vertex I should pay, that represents all the, or the total number of edges incident to vertex I. This represents all the edges which are incident towards the vertex I should be less than equal to the weight of vertex I. Okay, so the weight of the vertex I, this is a fairness condition. With that condition we can run the approximation. Clear? So for each vertex I, so we should say whatever the cost assigned, or whatever the age, whatever the weight assigned to an age should be less than equal to the weight assigned to a vertex. This is a fairness condition. Okay, the fairness condition says, in this example I have kept one example. This content basically I have kept from the Princeton University. This is a PPT followed by the faculty members or lectures there, from the Tardos. Okay, the book written by the Tardos and other co-author. Okay, so there I have also, I'll keep those resources there in a description, you can find it out. Okay, so 2 4 9 2, these are the vertices, four vertices with four different weight assigned here. Suppose I'm just focusing on this as our ith node. Okay, for this node we have uh, three incident edges, though it's undirected. So undirected means it's a bidirectional in sense. You just think there are incident, means three incident edges we have. So the main factor here for the fairness condition means whatever, suppose you are having 0 0 2 initially, so definitely we can say for 2 it is here 2, and one of them means 2 plus 0 plus 0, means this is pricing of the edges connected. If it is less than or equal to, then only we can say it is following the condition of fairness condition it should follow. Clear what it exactly says. If you are following the tight condition, it should be equivalent to the weight. This side is weight assigned to the vertex. Clear, this is what exactly it is getting used here. The whatever the values we are having, that should be at least 2. If you are saying 1 also, okay, if you are saying 1, so definitely I must tell you 2 is greater than equal to 1. So definitely we can say it follows the uh, a fairness condition. If it is 3, na, 3 is not less than equal to the 2. That's why we cannot say it's a fairness condition. That's why either 2, or might be this side is 1, this side is 1, this side is 0, or means this side is 0, this side is 1, it's good. Or else this side is 2, this side is 1, this side 2, 0, 0, means we are indirectly getting equal to sign or less than that. Definitely we can expect the value to be a our fairness condition. Clear. So next is we're getting is fairness condition. If you're getting is tight, it should be equivalent to. If it is tight, this represents tight situation. We will be discussing that one. Instead of getting less than equal to sign, we should have to get equal to sign. If equal to sign is getting used. Okay. Next, fairness lemma, if you're going to discuss, or subset the vertex cover set is, we are having any pair prices PE that should be less than any pair of vertex that should be less than any fair price which is an age is providing that should be less than the weight of the vertex cover set. Means we have found out, suppose for this condition, if I'm keeping 2 and I'm just keeping 9, so it is 11. And if I'm keeping 2, 2 and 4, it is 8. So the 8 is, the total 8 is here the W of S, that represents the cost of all the vertex. This is what a vertex cover basically. The weight of vertex covers is called as W of S. So this one should be at least greater than equal to each of the age, the value of the age assigned there. Clear? The proof represents, how do we prove it then? So this PE is representing as a small e, means a single e which belongs to set E. Here I have kept, this is one you know I kept this example for you to understand. The capital E is a set of edges. Here if I'm just keeping of small e, A to B is small e here. Clear? So A to B is small e. Here this is also considered as small e. So like this it is said to be a small e, and this cost, how do we find it out? If you are focusing on this one, like all the edges within that we have decided. Next target is, if all the vertices inside the set vertex cover, inside the vertex cover is, if all the vertices we are focusing on at least one endpoint, so definitely what we are getting, it is more than equivalent to the price of an edge. If you're focusing on one edge, if you are adding of all the vertices, like here it is written also, each edge E covered by at least one node S, means whatever the edges that we have, if it is at least covered by one of the vertices, means the repetitions could be there. If the repetitions could be there, it is definitely greater than equal to the cost of the edge. Okay, this is what it is written. So this one, as per the fairness condition, it is equivalent to the weight assigned to I. Clear? Next, this is your all those all the vertices within the vertex cover. Like if you are going to add it, this is what your W of S. Clear? This is your weight you gained from the vertex cover, or the vertices inside the vertex cover which you have got. I think it's clear to you. Next, pricing method, what we have discussed. I kept one algorithm for you to understand. S is a set where in future we are keeping those vertices which are being said to be our vertex cover. Okay, so S is vertex cover. Set initial it is 5, nothing is there initially. For each, here we are trying to set for each edge, we set the pricing as 0, as we have already said the pricing is the cost assigned to each edge. We set it is as 0 for us for our file. Next loop, which is while loop we have used. Here what exactly we have to do, there exists an edge such that neither I or j is tight. Tight represents this condition. If you are saying the fairness condition, for fairness condition I must tell you the E equivalent to I comma j means this is your condition, which is the cost should be less than equal to W of I. Here you are expecting, for fairness condition you are expecting the approximation, but for tight condition you are going towards the optimal. For tight condition means definitely the value which you have, like here this is like 1 and 1 you are getting 2. Clear? If you are having 0 1, so it is nearly equivalent to something you are expecting, which is your fairness condition. But here the tight we have to find out. Why? Because our target is towards optimal. So next, select such age, whichever the age that you have selected, that you have to select, and increase the cost. Basically the price inside the age has to be increased in such a way that at least you should reach any of this, either I or j, you have to reach are equivalent to the value or the weight assigned to I or weight assigned to j. You have to increment the cost of the age. Okay, once you found all the weights, or sorry, all the edges have been already being found out as like all the sets we found out or all the vertices we found out as tight, then we stopped it, then we terminated. Then what we did, like S, all the tight nodes will be assigned to like whatever the tight nodes that we found. Tight means the vertex cover which we found indirectly, we kept in a S, and that we have to return S. Whenever we are returning S, this represents the vertex cover for us using the pricing method. Okay, so the this method basically provides us the complexity in a polynomial time, as you have seen it. Based on the edges basically we are focusing on, that's why it is the number of edges. It gives us the polynomial time complexity here. Next, as we have already discussed how it is getting used, now the example says us, this is one graph given to us where there are 4 nodes A, B, C, D, okay, with certain ages like are there, as well as certain weights assigned to each the vertex. So the weights are like 3, 4, 3, 5, okay. Any of this, as for the first algorithm says, we have to first initialize with 0. Okay, these are considered as a 0, weights are considered as 0 now. So this is an initial condition. Next is we have to select any of the age which is not yet tight. Tight means we need to equivalent to any of the endpoint. If you are picking this age, so you at least it should be equivalent to this, or it should be equivalent to this. Then only we can say we have stopped it, or maybe we say it is tight. So as per the example, they have said they have targeted this age. This age has been targeted at the first stage. So what they have to do, though it is not equivalent, this value is not equivalent to either B or either A, what they have to do, like they select this age and they try to increase the PE value, means the price has to be increased. Next, the price has to be increased by 1, okay, as it is written like the until it is 1 by 1, like we are increasing 1. It will check whether it is equivalent to this or not. No, so we will be increment to 2, it will be checking, then no, then 3. So or direct you can switch to any of this, because it started with a 0 as with the algorithm. It's just for layman perspective we have written. So you can switch to any of these endpoints. Suppose for this we found it is as 3. Once we found this is as 3, so it is equivalent to the node, means this age is equivalent to the weight of this vertex. Any of the endpoint of the vertex means it is tight. Clear? So this condition For this condition I'm just writing this age. For B I'm just writing E belongs to set E, PE, that should be less than W if it is there, so it is called as fairness condition. If you want to find the weight tight condition, it should be equivalent to the weight. So how do we say then W of V equivalent to price of AB, this A to B, price of A to B plus price of, because these are two incident ages, so price of B to C. Clear? If you are incrementing this one by targeting this age, so if it is 3, so you must be said as 3 equivalent to, if it is said to be 3, so you say this is tight now. If your setting is tight, one if it is selected, another has to be discarded. Clear? Because these are two incident ages towards the vertex. Next I am just highlighting it, like we have selected this one as our tight node, means this is one of our vertex cover we have selected, minimum weighted vertex cover. Next we have three options, which one to be select you can decide as for your choice. But as for the PPT, they started with this age, so that's why what we have to do, like for this age we can have already incident 1, 2 and 3. There are three incidents. Clear? For three incidents we have already selected, as to make it tight we have already 3. So any of this will be enhanced to at least 1, because if for this side, then only we can say 4 will be our tight condition we can expect. Clear? Then only we can say for getting a tight condition we can say it should be at least 1, then only we can get it tight. Clear? Next, making it tight, once we have done it, so we said it should be our selected set. Then clear? Next, once we have selected this one, so we have to remove the connected only. Okay. Next we have only one which has to be selected. If you are going to select this one, already one is, like if you are going to select this age, so already one is there. Is for this condition I'm just writing 3 is equivalent to weight of this one, weight of D, weight of D is 3, is equivalent to cost, which is 1 plus 0 is there. So to make it 3 we should have to take this as 2. So definitely we can say 3 is equivalent to 3. This is our tight condition. Clear? So the 2 we are saying, so we can directly get from this, because we have to keep this as tight. Okay. So W of A, this is W of B is weight assigned to B. Clear? So in this way we found the vertex cover, the minimum weighted vertex cover, which is our as per the value it is 3, then it is 4, which is tight A. Then this is also a tight D, which represents as our approximation approach, using basically we have used pricing method to find the minimum weighted vertex cover. So here the minimum weight you have got as 3 plus 3 is 6 plus 4 is 10. 10 is your answer. But if you are just focusing as 10 is your answer, there is other option also. If you think this is a better option, but the optimal is you can pick this 4 and 5. Definitely it's a vertex cover, but the weight is 9, which is a clear cut idea that we are getting. So definitely the approximation is uh, more than the optimal solution. Then how much it is more, that we are going to discuss. Clear? It is written as per the theorem. It is two approximation for weighted vertex cover. It is asking. Okay. It just have a doubt whether it is two approximation or not. we have to prove it. Before proving, like, we should know the algorithm will terminate if at least one node becomes tight after each iterations of the while loop. Then we are just picking that node to s, that we have already discussed here. While loop we are running. Once we are finding at least any of this is tight, means it is equivalent, then we are just adding to that s. This is written here. Clear? Next, S represents the set of all tight nodes, means the vertex cover which you found, this is S. Next, S star is optimal vertex cover, which we recently discussed just for an example. Okay. Next, how do we say it is 2 times more than the optimal solution? 2 times equivalent to or more than the optimal solution. How do we say? Let us think for it. Whenever we're finding out the weight of the weight assigned to the vertex cover of the set S, which is there, like the number of vertices are 4, 5, 7, what are the vertices are, the total weight is our vertex cover, weighted vertex cover. Once you are going to find it out for S, I will be the, it belongs to the set, and each weight will be added. This is what a mathematical representation of it. Like there are, suppose there are 4 vertices, you can check the 4 vertices belongs to the total set is 4, so the weight assigned to each vertex you just add it using sigma. This is what it is written. Next is for all nodes in S. So you are finding the value assigned to that one. So as we have already discussed, this w1, this pe, fairness condition, pe is less than equal to wi. Clear? This is what we are also using this condition. We have converted this fairness condition to this condition. This is your fairness condition. Clear? This is your fairness condition. I'm just writing in short is FC. Fairness condition. We are trying to find it out. That this time you can also take greater than equal to sign also, but equal to sign they have kept. Where we are just having this one, like whenever we are finding the weight assigned to the vertex, it should be greater than equal to the edges assigned towards the vertex. Clear? Next, if you want to check for all the vertices, like it is within the set vertex cover, if you want to check all the vertices, definitely, suppose I am going to that example which we started with. Suppose S we have found out as AD. Clear? S is AD for us. Here the vertices are more than 2 times. Here I am saying it is S is 2, V is 4, means I am focusing on S. Within S, it is just half of the total number of vertices. This is what it says. Clear? Once I am collectively adding this one instead of this, so within S we have, and as per the example we have A and D, there is 2 elements, but in a vertex cover we have 4 elements or 4 vertices. So if I am using this, so 2 times in general also, if you can check this example also, A to B, suppose I am focusing only one endpoint, it is for checking whether the edge is covered or not. For one endpoint, it is, you can say, it is for one time. But if I am focusing on other endpoint also while checking whether the edge is covered or not, it is 2 times, as we have already seen earlier. Clear? So this is what it says. It gives you 2 because of this reason. Each is counted twice. That's why you are getting with the 2 value. Clear? And rest of the things as it is. And though it is tight, for a while we are focusing on the tight, that's why it is our optimal weighted vertex cover we are expecting. Though it is tight, I'm just writing it, though it is tight, that's why you are expecting the value should be the optimal weighted vertex cover you are expecting. So in this way, what we found out, The WS, which is the set cover, the weight of the say vertex cover that you found, is less than equal to 2 times the weight of the optimal vertex cover, which is 2 approximation. So I hope it is clearly understood by you. If any doubt, please comment below and have a good day.